The provided Python code snippet imports necessary libraries and modules for a data science project, but does not actually perform any data processing or machine learning tasks. The imports cover various functionalities. 1. OS is used for interacting with the operating system, particularly for file and directory operations. 2. Pandas is a data manipulation and analysis library, often used for working with structured data like CSV or Excel files. 3. Matplotlib.pyplot and matplotlib.patches are part of a library for creating static, interactive, and animated visualizations in Python. 4. Seaborn is a statistical data visualization library based on Matplotlib, providing a higher-level interface for drawing attractive and informative statistical graphics. 5. Warnings is a module for managing warnings, which allows the codemer to suppress or output warnings that could be raised during execution. 6. NumPy is a fundamental package for scientific computing with Python, providing support for large, multi-dimensional arrays and matrices, along with a collection of mathematical functions to operate on these arrays. 7. Importlib.reload is used to reload modules. This can be helpful if you've made changes to your module files and want those changes to be reflected without restarting the Python interpreter. 8. Sklearn.naivebayes.gaussianNB allows the use of the naive Bayes algorithm for classification tasks, where features are assumed to have a Gaussian distribution. 9. XGBoost.xgbc classifier is a part of an optimized gradient boosting library that provides a powerful machine learning algorithm, XGBoost, which is widely used in winning machine learning competitions. Additional lines in the code snippet set some configurations. Warnings are turned off via the warnings.filterWarningSignor command to prevent the output of warnings during code execution. The Matplotlib configuration for figure resolution is set to a specific DPI dots per inch that suits the native screen resolution of the developer's computer using plt.rc_params = 27. The purpose of this code block is to set up the environment with necessary tools for data processing, visualization, and machine learning. However, this snippet by itself does not execute any analysis or machine learning. It just prepares the Python environment for those tasks by importing relevant libraries and setting initial configuration parameters. The Python code snippet provided imports various functionalities that are commonly used for time series analysis in Python, specifically those from the stats models library, which provides classes and functions for the estimation of many different statistical models. Firstly, ARIMA autoregressive integrated moving average is being imported. This is a popular statistical method for time series forecasting that captures different aspects of the data, like trend and seasonality, by combining differencing to remove trend, autoregression to capture correlation with past values, and moving average to capture correlations with past errors. Following that, Sarimax seasonal autoregressive integrated moving average with exogenous factors is imported. This extends the ARIMA model by incorporating seasonality and the potential impact of exogenous variables, external factors that could influence the time series data. Next, the code provides functionality for plotting, specifically the partial autocorrelation function plot_pf and the autocorrelation function plot_acf from stats models. These plots are used to identify the lag in the data, which is an important part of model identification in time series analysis. Further, the code snippet imports several evaluation metrics from Sklearn.metrics, namely mean squared error, confusion matrix, F1 score, and accuracy score. These are used to evaluate the performance of statistical models and machine learning algorithms on tasks such as regression and classification. Lastly, the autocorrelation plot from pandas.plotting is imported, another tool to visualize and identify the presence of correlation in a time series dataset. The overall purpose of this code is to set up an environment for performing sophisticated time series analysis and forecasting tasks with an emphasis on ARIMA-based models, allowing the user to both build and evaluate these models as well as analyze the time series data through visual diagnostics. This Python code snippet is related to the setup and configuration of a neural network model using TensorFlow 2.0, particularly employing its integrated Keras API for model construction. TensorFlow is a widely used open-source library for machine learning and artificial intelligence tasks, with Keras being a high-level neural networks API that can run on top of TensorFlow, designed to enable fast experimentation. The code begins by importing necessary components from TensorFlow's Keras package, such as sequential and model for constructing the models, various layer types like input, flatten, time-distributed, LSTM, dense, bidirectional dropout, conv-LSTM-D, conv1D, global max pooling 1D, max pooling 1D, convolution D, batch normalization, and leaky Ryu, which are used to build different layers of a neural network model. Furthermore, the code imports armsprop, which is a type of optimization algorithm used to update network weights iteratively based on training data. The inclusion of Bayesian optimization from the BayesOp package suggests that the code intends to optimize hyperparameters using Bayesian optimization, a strategy for finding the maximum value of an objective function that is expensive to evaluate. This approach efficiently optimizes the hyperparameters of the model by building a probabilistic model mapping hyperparameters to a probability of a certain objective score, and uses that to pick the most promising hyperparameters to evaluate in the true objective function. The mention of plot model suggests the code may be intended to visually represent the architecture of the neural network, which can be helpful for understanding and debugging the model structure. Overall, the purpose of this code is to set up the groundwork for building and tuning complex neural network models with various types of layers, and to optimize their performance using advanced techniques like Bayesian optimization. Additionally, it sets up visualization tools to aid in understanding the constructed models. This Python code snippet likely indicates the start of a script where the codemer imports modules or specific functions from other files or libraries into the current script to use their functionality. The import functions part suggests that there is a file named functions.py, which contains various functions that the codemer wants to use in the current script. When this file is imported, all the functions and variables defined in functions.py become available to use. The import plotting implies there is another module named plotting that provides capabilities, presumably for generating plots or graphs. The purpose of importing this would be to visualize data or results in a graphical manner, using the functions and classes defined within the plotting module. The overall purpose of importing these modules is to reuse code, which helps in keeping the current script clean and manageable, and to use the functionalities provided by these modules without having to write the complex logic from scratch. It's a common practice in code to organize code into modules that can be easily imported and used across different parts of a project or even different projects, improving modularity and maintainability. The provided line of Python code is used to set the seed for the random number generator provided by the NumPy library, which is a Python library widely used for numerical computations. The seed is a starting point for the sequence of pseudo-random numbers, which means that using the same seed will allow for the generation of the same sequence of numbers each time the code is run. The purpose of setting a random seed is to ensure reproducibility in scientific computing and other applications where it is necessary to obtain the same results across different runs of the code, such as in simulations or when the random behavior needs to be debugged. The specific value of 66, in this case, is chosen arbitrarily. Anytime this code is run, using this same seed, NumPy's random number generator will produce the same sequence of numbers, assuming the same version of NumPy is used, and the same subsequent random number generating functions are called in the exact same order. Setting a seed is particularly useful for sharing code with others, or for creating examples for tutorials or teaching, where consistent results are imperative. This Python code snippet is designed to read multiple CSV files from a specified directory, in this case, data/stocks, and then to process and store their contents into a dictionary. The script starts by using the os.listdir function to get a list of all files within the data stocks directory. It then initializes an empty dictionary named stocks, which will be used to store the data from the CSV files. In the next step, the code iterates over every file in the obtained list of files. Within the loop, it checks to see if the file extension is CSV, indicating that the file is a CSV file. If the file is a CSV file, the code splits the file name at the period to separate the name from the .csv extension, and the name part of the file without .csv is used as a key in the stocks dictionary. It then reads the CSV file into a pandas data frame using the pd.readCSV function, with the date column set as the index of the data frame. After reading the data, the script converts the index, which is the date column, to a pandas datetime object to enable time series operations, and assigns this data frame to the corresponding key in the stocks dictionary. The purpose of this code is to automate the loading and organization of stock data files for further analysis, potentially on time series data, given that the date column is structured as a datetime index. The resulting stocks dictionary provides a convenient way to keep the data from each CSV file associated with its respective stock name, making it easier to access and work with specific datasets as needed. The given Python code defines a function named baseline model, which takes an input parameter stock, expected to be a series or array representing stock data. The function's purpose is to create a simple baseline prediction model for a binary classification task related to the stock data, where it will make random guesses between 0 and 1 inclusive for each element in the input stock array. The function works by first generating an array of random integers, where each integer is either 0 or 1. The length of this random array is the same as the length of the stock input, ensuring that there is a one-to-one correspondence between the random predictions and the true stock values. Next, the function calculates the accuracy of these random predictions by comparing them with the actual values of the stock data that have been processed by a binary transformation function, functions.binaryStock. This binary function is presumably used to convert the stock data into a binary format 0 or 1, compatible with the baseline predictions, but its implementation details are not provided. The accuracy score function, likely imported from a machine learning library such as scikit-learn, is used to measure the proportion of correct predictions, how many of the random guesses match the true binary values of the stock data. Finally, the baseline model function returns the calculated accuracy score, which represents the performance of this baseline model with random guessing. This score can be used as a starting point to evaluate the effectiveness of more sophisticated predictive models by comparing their accuracy against this random baseline. Essentially, it sets the lower bound of performance. Any meaningful model should outperform this random guessing approach. The provided Python code snippet evaluates the accuracy of a model, potentially a basic one termed as a baseline model, against the returns of Tesla stock, labeled as TSLA, within a stock's data collection. The baseline model's function, baseline model, is executed by feeding it the return column associated with TSLA from the stock's data. The output of the function is a numerical value representing the model's accuracy, which is a measure of how well the model predicts or fits the given data. After the model's accuracy is computed, the code formats this value as a percentage and prints it out with a precision of 1 decimal place. The phrase baseline model accuracy precedes the formatted percentage, allowing users to easily understand what the printed value represents. Overall, the purpose of this code is to assess how accurately the baseline model performs on the Tesla stock return data and to present this information in a clear and interpretable manner. The Python code snippet provided carries out a simulation exercise to evaluate the performance of a baseline model function using the return values of Tesla stock indicated by stock's TSLA return. The code creates an array, basepredz, which is used to collect the predictions from the baseline model. The simulation runs for 1,000 iterations, where each iteration involves calling the baseline model with the Tesla stock return values to generate a new prediction, appending the result to the basepredz array. Once the simulation is complete and all predictions are collected, the code creates a histogram to visualize the distribution of the predictions. It sets the figure size to 16 inches by 6 inches and applies a predefined seaborne white grid style for a cleaner and more readable appearance. The histogram bins the data into 50 parts, with the bars colored in a specific blue shade num4ac2fb. A title is added to the histogram, and the average mean value of the predictions is indicated by a vertical dashed line to provide a point of reference for the central tendency of the model's predictions. Finally, the visualization is displayed using the peltshow command, allowing the user to analyze the spread and centralization of the baseline model's predictions visually. The purpose of this code is to allow a user to assess how often the baseline model returns certain prediction ranges and to determine its average prediction value, which can be an essential step in evaluating and comparing the accuracy of different prediction models in quantitative finance. The Python code provided appears to belong to a larger context where there is a variable stocks, likely a dictionary that holds data related to stock information. Within this dictionary, TSLA seems to refer to Tesla's stock data, and it seems to be stored as a pandas data frame given the use of .shape0 and return.head. The code snippet does two main things. First, it prints out a message that includes the number of entries related to Tesla's historical data. It does this by accessing the data frame corresponding to the TSLA key in the stocks dictionary, and then it gets the number of rows in this data frame with stocks TSLA, shape 0. The number of rows represents the number of entries or data points. The format method is then used to insert this number into the string, and the result is output to the console. Second, after printing the message, the code retrieves the first few entries, typically 5, as this is the default for .head method of the return column from the TSLA data frame. This is achieved by subsetting the data frame to only include the return column and then using the .head method to get the first few rows. The result of this operation is typically displayed in the console or interface from which the script is being run. In summary, the purpose of this code is to report on the size of the Tesla historical data in a dataset, and then to display a small sample, the first few entries of the return information from that dataset. This would be useful for a quick check to confirm that the data is loaded correctly and to get an initial sense of what the return values look like. The mentioned Python code is intending to use the plotting capabilities of the matplotlib library in combination with the functionality of the statsmodels library to visualize the autocorrelation in the returns of Tesla's stock price. Initially, the code sets the default size of the figure for plots using the matplotlib library's rc-params configuration dictionary. The key figure.fig size is given a tuple that specifies the width and height of the figures that matplotlib will create. In this case, the figure will be 16 units wide and 3 units tall. Next, the plot_acf function from the statsmodels library is called. This function creates an autocorrelation plot, which graphs the autocorrelations of the series provided at different lags. The series that is targeted for autocorrelation plotting is stocks TSLA. Return, which suggests that there is a data frame stocks containing the returns of Tesla's stock, indicated by the key TSLA, and within it, there's a column or a key named return that holds the actual return values. The lags parameter is set to range 300, which means autocorrelations at lag values from 0 to 299 will be computed and displayed. This parameter controls how many time lags should be considered when calculating autocorrelation. In financial time series analysis, investigating the autocorrelation can help identify any serial correlations in the returns, which might suggest patterns that could be modeled for predictions or understanding the return behavior. Finally, plt.show displays the plot. This command causes the figure to be rendered and shown on the screen, allowing the user to visually inspect the autocorrelations of Tesla's return series. Autocorrelation plots are useful in understanding the time series data, particularly in identifying any seasonality or time-based patterns within the data. The code is designed to evaluate the performance of different autoregressive integrated moving average ARIMA models in predicting stock returns. ARIMA is a popular statistical method used for time series forecasting. The code defines a list of ARIMA model specifications referred to as orders, which consist of 3 elements, P, D, Q. The P represents the number of autoregressive terms, D is the degree of differencing, and Q is the number of moving average terms. These tuples represent different model structures that the code will test. The dataset containing the stock returns is split into a training set and a testing set. The train variable contains an array of historical stock return data, and the test variable contains data points that the model will attempt to forecast. For each ARIMA order specified, the code performs the following steps within a loop. 1. It creates a copy of the training data. 2. It proceeds to iterate over each data point in the test set where the actual forecasting happens. In each iteration, it initializes an ARIMA model with the current order and the historical data, which includes all of the training data and, progressively, data points from the test set. The model is fitted to the data. A prediction for the next time step is generated. The predicted value is stored, and the actual return value from the test set is appended to the history to gradually build a dynamic forecast, simulating a real-world forecasting scenario where new actual data points become available over time. 3. The loop records individual predictions for each order in order predictions. After predictions for all orders are made, the code calculates the accuracy of each model by comparing the binary representation of the actual and predicted returns and prints the accuracy percentage. The binary function mentioned in the code presumably converts continuous returns into a binary format, such as indicating an increase or decrease, which is required for calculating the accuracy metric. If, at any point, the code encounters an issue with an ARIMA order, such as non-invertibility or non-stationarity of the series after differencing, it will print a message indicating that the specified order is wrong and continue. Finally, the predictions for each ARIMA model are stored in a dictionary called all predictions. This structure maps each ARIMA order to its corresponding list of predictions, thereby allowing further analysis or evaluation of the model's performances. The provided Python code is for visualizing data using matplotlib, a plotting library in Python. It creates a series of plots to display time series data for some variable described as returns over days. It appears to compare 2 different datasets, actual test values and predictions made by an ARIMA model. Initially, the code generates a big plot with a set figure size. It then plots 2 lines on the graph, one representing the test data and the other representing prediction data from the ARIMA model. The colors for these lines are specified using hexadecimal color codes. A legend is added to help differentiate between the test and prediction lines, with settings for position, number of columns, font size, and padding. The title of the plot, as well as the labels for the X and Y axes, are set with specific font sizes. The title indicates that the graph is showing ARIMA model predictions. An arrow is annotated on the plot, drawn from one point to another with specific coordinates, font size, and look defined by the given arrow properties. This could be used to draw attention to a specific feature or portion of the graph. A patch, specifically a rectangle, is then added to the plot. This patch is situated at defined coordinates, has a dashed line style, a particular line width, and filled color. It likely highlights a specific area of interest on the plot, providing visual emphasis. In addition to the main plot, a small inset plot is created within the larger one. It shows a zoomed-in view of the first 30 data points of both the test dataset and the ARIMA predictions, repeating the color coding scheme used in the larger plot. This smaller plot, however, excludes axis labels to simplify the presentation. Finally, the complete visualization, with both the large plot and the inset, is displayed to the user with plot show. The code is designed to provide a comprehensive, comparative view of actual test values against predicted values from a statistical model, with visual annotations and a subset view for detailed examination. This Python code snippet is creating a visual representation, specifically a histogram, of the distribution of real and predicted stock return values using matplotlib, a plotting library. The purpose of the code is to compare the true returns of Tesla TSLA stock to the returns predicted by an ARIMA autoregressive integrated moving average model. The code starts by setting up the figure with a specific size. It then proceeds to plot two histograms overlaying each other. The first histogram represents the actual returns of TSLA stock for a selected range of time, specifically data points from index 1900 to 2300. The data are adjusted with reset index, implying that the data might be part of a larger data frame and need to be realigned for proper plotting. The second histogram shows the distribution of the predicted returns, which are presumably generated by an ARIMA model, indicated by the variable name allPredictions. The parameters 0, 1, 0 likely refer to the order of the ARIMA model. A common notation in time series analysis, where the numbers correspond to the AR, I, and MA components respectively. A vertical dashed line at 0 on the x-axis is added to serve as a reference point, possibly to indicate the point of no return or a threshold between positive and negative returns. Furthermore, the plot is titled to reflect that it's comparing true versus predicted values from an ARIMA model and is appropriately labeled. Lastly, a legend is added to distinguish between the two histograms, and the plot is displayed with pelt.show. Overall, the code is used for analyzing the performance of the ARIMA model by comparing the distribution of predicted stock returns against the true stock returns, which is a common practice in financial analysis to evaluate forecasting models. The provided Python script is designed to process financial data related to stock market activity, particularly focusing on the stock TSLA, likely Tesla Inc. The script is aimed at applying a binary classification to the stock returns, comparing predicted classifications to actual ones, and then assessing the performance of the classification model. Initially, the code selects a subset of Tesla's stock return data from index 1900 to 2300, and then applies a function to convert these real-valued returns into a binary format, likely indicating whether each return is positive or negative. This process generates test binary, a series of binary values representing the actual outcomes over a specific period. Next, predictions previously generated by some model are similarly converted into binary format using the same binary function, resulting in trains binary. This represents the model's predictions about whether the stock returns would be positive or negative. With both actual outcomes, test binary, and predicted outcomes, train binary, in hand, the code calculates the confusion matrix and extracts the true positives TP, true negatives TN, false positives FP, and false negatives FN. These values are key metrics for evaluating the performance of binary classification models. The script then calculates the overall accuracy of the predictions, which is the number of correct predictions, both positive and negative, divided by the total number of predictions made. Finally, the script prints out the count of true positives and negatives, correct predictions, the count of false positives and negatives, incorrect predictions, and the accuracy percentage, providing a concise evaluation of the model's performance in predicting the binary outcomes of Tesla's stock returns for the selected period. The provided Python code snippet is performing a task related to data handling with the use of the pandas library, which is a popular data analysis and manipulation library for Python. The snippet reads the contents of a CSV, comma-separated values file named Tesla headlines.csv that resides within a folder named data. This file likely contains a collection of headlines and possibly other related information that pertains to the company Tesla Inc. The function pd.readCSV is used to load the data from the CSV file into a pandas data frame. A data frame is a two-dimensional, size-mutable, and potentially heterogeneous tabular data structure with labeled axes, rows, and columns. It's akin to a spreadsheet or SQL table, and it's the primary data structure used in pandas for data manipulation and analysis. One important parameter in this function call is index co=equals date, which specifies that the column labeled date in the CSV file should be used as the index of the resulting data frame. The index of a data frame is a key concept in pandas, as it gives us a way to access and manipulate data efficiently. By setting the date column as the index, the code implies that date information is significant, suggesting that the headlines are likely timestamped and that the chronology is relevant for the purpose of the analysis or manipulation being performed on the dataset. The purpose of this code is to set up the data frame for further analysis or manipulation, such as sorting by date, filtering based on certain criteria, time series analysis, or extracting specific information about Tesla from the headlines over particular time periods. This action is a common initial step in a data processing or analysis pipeline. This Python code snippet is designed to manipulate financial stock data and related news sentiment for Tesla, indicated by the TSLA stock ticker. The code assumes there are two data structures available, stocks and Tesla headlines. Stocks is likely a dictionary-like structure where each entry is indexed by its stock ticker. In this case, stocks TSLA refers to a data frame, a tabular data structure provided by the pandas library containing the stock information for Tesla. Tesla headlines is another data frame that presumably contains news headlines associated with Tesla, including a date column when the news was published and a sentiment column which quantifies the sentiment of the news headlines positive, neutral, or negative. The data frame Tesla headlines is being grouped by the date, meaning the sentiment data is aggregated for each unique date. The .mean function is called on the grouped data, which computes the average sentiment score for each date. After the averaging operation, the result, a new data frame with average sentiment scores per date, is joined to the stock.stat data frame using the .join method. This method combines the stock data with the sentiment data based on the index, which in this case is likely the date. If the indices match, the corresponding average sentiment score for each date is added to the stock.stat data frame. The purpose of this code is to merge financial stock data with averaged news sentiment scores on a per-date basis. This could be useful for financial analysis to determine the potential impact of news sentiment on stock performance. By appending sentiment scores to the stock data, the analysis can include the insights from news sentiment alongside traditional financial metrics. The code snippet provided is a line of Python code that utilizes the pandas library, which is a powerful tool for data manipulation and analysis. Specifically, this line of code is addressing the issue of missing data within a data frame named Tesla. In pandas, the fillna function is used to replace missing or nan dice, not a number values within the data frame with a specified value. In this case, the specified value is 0, which means that all occurrences of missing or nan values within the Tesla data frame will be replaced with the integer 0. The in_place=true parameter is especially important in this context because it determines how the operation is performed. By setting in_place=true, the code is instructing pandas to perform the replacement operation in place, which means that it will modify the Tesla data frame directly, rather than returning a new data frame with the missing values filled. This has the advantage of not requiring the assignment of the result to a new variable, thereby saving memory and keeping the code concise. The purpose of this code is to clean the data within the Tesla data frame by ensuring that there are no missing values, which can be problematic for various data analysis or machine learning algorithms that require complete datasets. By filling missing values with zeros, the dataset becomes more uniform and potentially easier to work with, although the choice of filling with 0 might depend on the context and suitability for the particular analysis being performed. This Python code snippet is designed for visualizing financial data, specifically to compare the news sentiment and daily returns of Tesla stock within a certain time frame from January 10, 2019 to September 5, 2019. The code begins by setting a visual style for the plots using the Seaborn white grid, which is known for its clean and informative style, suitable for statistical graphics. It then creates a figure with a specified size to ensure the plot is large enough to comfortably visualize the data. Two lines are then plotted on the same chart. The first line represents the sentiment of news articles about Tesla, which has been shifted by 1 day to presumably align or compare it with the stock's return on the following day. The second line represents the return of Tesla stock, which is a measure of the stock price change over the specified time period. Both lines are plotted with specific colors to distinguish them, and labels are attributed for legend purposes. The plot legend command adds a legend to the figure, which helps in identifying each line with its corresponding label. The legend's appearance is customized for aesthetics, including a semi-transparent frame and a fancy box style. A title is added to the chart, providing a clear indication of what the plot represents, a comparison between Tesla's news sentiment and daily stock returns. Finally, plt.show renders the plot, which will display the line chart on the screen. The purpose of this code is to offer an intuitive visual representation for analyzing the potential relationship between public sentiment from news articles about Tesla and the stock's performance. This could be useful for financial analysts or investors who are trying to understand how media coverage may influence stock prices. This Python code is using the pandas library to create a data frame that captures the relationship between two sets of data, sentiment and return, both of which are presumably columns in another data frame named Tesla. The Tesla data frame contains time series data indexed by date. The code first selects a subset of the Tesla data frame, filtering rows based on a date range from January 10, 2019 to September 5, 2019. Within this subset, two series are created. 1. Sentiment. This is the shifted version of the sentiment column from the Tesla data frame, effectively moving each value up by 1 row. This means that the sentiment value for any given date is actually the sentiment from the previous day. The shifting of data is common in time series analysis, often used to compare a value with its previous value or to create lagged variables as features for predictive models. 2. Return. This is simply the return column from the Tesla data frame corresponding to the same filtered date range, with no shifting applied. After creating a new data frame with these two columns, the code then calculates the correlation matrix for the data frame using the .core function. The correlation matrix provides a statistical summary of how closely related the sentiment values are to the return values. It contains correlation coefficients that range from -1 to 1, where a value close to 1 would indicate a strong positive correlation, a value close to -1 would indicate a strong negative correlation, and a value close to 0 would suggest no linear correlation between the two variables. In summary, the purpose of this code is to examine the linear relationship between the sentiments on one day with the stock returns on the next day for the Tesla data within the specified date range. The outcome helps to understand whether there is any linear predictive power of one day's sentiment on the next day's stock return. This Python code snippet is utilizing a scale function from a module or package named functions. The function is being applied to a specific element TSLA, which is extracted from a dictionary or a similar data structure named stocks. The TSLA key refers to data that, in the context, is likely related to the stock price of Tesla, Inc. The purpose of the scale function is to normalize or scale the Tesla stock prices, converting them into a predefined range, between 0 and 1 in this case. Normalization in this form is often performed as part of data preprocessing before the data is used in machine learning algorithms. By scaling the data to a 0-1 range, it ensures that the Tesla stock price data is on a similar scale to other variables that may be considered, which can improve the performance of many machine learning algorithms. This can be particularly important when dealing with features that are on vastly different scales. In summary, the code snippet is preparing the Tesla stock price data by normalizing the values to be between 0 and 1, using a provided scaling function for potential use in further data analysis or machine learning tasks. The code snippet is part of a sequence of operations likely involved in preparing data for a machine learning task or statistical analysis, specifically predicting stock returns. The variable x is assigned a scaled version of some time series data related to Tesla, indicated by the TSLA identifier, with the scaled TSLA -1 expression. The -1 part suggests that we are interested in all the data except for the last entry. This slicing is commonly done when constructing features for a predictive model, where you want to predict the next data point based on the previous ones. the variable y is set to the return column from a data frame stocks indexed by TSLA. The method shift1 is used to move the data up by one position, which effectively aligns each return value with the previous day's data since we're leaving out the last value from x. Again, mash1 is slicing the shifted series to exclude the last entry to ensure that the dimensions of y match those of x. The purpose of this code is to create two aligned datasets, x, which could be the features or independent variables without the last data point, and y, which is the target or dependent variable, the next day's stock return, without the last value because there is no next return for the final entry in the original dataset. These prepared datasets are typically used to train a model to predict future returns based on the given features. The snippet of Python code provided is utilizing a machine learning library known as XGBoost to initialize and train a classification model. XGBoost, which stands for Extreme Gradient Boosting, is a popular and powerful library designed for performing gradient boosting on decision trees, which is useful for a variety of machine learning tasks. The first line of code creates an instance of the XGBoost classifier. This class is designed for classification problems, where the goal is to predict a discrete label or class for each instance in a dataset. The instance is stored in the variable XGB. The second line of code fits or trains the model on a given dataset. The fit method is used to train the model using features and labels. X1500 specifies all the rows from the 1500th row to the end of the X dataset and is used here as the feature set for training the model. Features are the data attributes used to make predictions. Y1500 represents all corresponding labels for the training dataset from the 1500th entry onwards. Labels are the actual outcomes that the model aims to predict. The purpose of this code is to prepare the XGBoost classifier model by training it on a subset of a larger dataset so that it can be used to make predictions on new, unseen data. Typically, after this step, the model's performance would be evaluated using another subset of data that was not used during the training phase, i.e., testing data to understand how well the model generalizes to new information. The Python code snippet is used for visualizing the importance of different features in a dataset that has been processed by an XGBoost model. XGBoost is a popular machine learning algorithm for regression, classification, and ranking tasks that handles structured data. Firstly, the code constructs a data frame named important features from x.columns and xgb.featureImportances. The x.columns provides the names of the features, whereas xgb.featureImportances contains the importance scores as determined by the fitted XGBoost model. These importance scores indicate how much each feature contributes to the model's predictions. Secondly, the newly created data frame is sorted in ascending order of importance, ensuring that less important features appear first and the most important features appear last in the data frame. Then, the script sets up a horizontal bar chart with specific figure dimensions and a white grid style. This bar chart is plotted using the sorted feature importance data with the feature names on the y-axis and their corresponding importance scores on the x-axis. The bars are colored with a specific shade of blue. It includes title and x-axis label with customized font sizes for clarity and aesthetics. Finally, the pl.show command is called to display the plotted bar chart. This visual representation helps in quickly identifying which features are more influential in the predictive model. By analyzing this chart, one can make informed decisions about feature selection or gain insights into the data structure as interpreted by the XGBoost algorithm. The purpose of this Python code is to prepare a dataset for time series analysis or machine learning forecasting. The dataset contains stock price information for Tesla TSLA, which is being processed to serve as input data features and output data targets for a predictive model. Initially, a variable n steps is set to 21, which indicates that the model will use a sequence of 21 consecutive data points to make a prediction about the next data point. Next, the Tesla stock price's stocks, TSLA, are scaled to a range between 0 and 1. This scaling is a common pre-processing step in machine learning tasks as it can improve the performance of the algorithms by normalizing the input data. The function functions.split sequences is then used to transform the scaled stock prices into sequences of length n steps. It also splits the data into training and testing sets based on a ratio with 0.8, meaning 80% of the data will be used for training and the remaining 20% for testing. The features xtrain, xtest are the sequences of stock price data. The targets ytrain, ytest are the corresponding future stock returns, which is the percentage change in stock price, which are shifted back by one time step so that each sequence is aligned with the return that immediately follows it. This setup is typical for supervised learning tasks, where the algorithm will learn from the training data, X-train and Y-train, and the performance will be evaluated on the testing data, X-test and Y-test. This Python code is a snippet for constructing a neural network model using the keras library, commonly used for deep learning tasks. The provided code is configured to create a sequence prediction model utilizing long short-term memory LSTM layers, which is particularly suited for time series or sequential data. At the start of the code, keras.backend.clear session is called to clear any previous model or layers that remain in memory, ensuring that you are starting with a clean state. This can be useful to prevent any potential issues with model training due to old states. The following lines define variables n steps and n features, which represent the number of time steps sequences and the number of features in each time step, respectively, that the model will expect as input. These values are taken from the shape of the training data, X-train. The sequential model is then instantiated, which denotes a linear stack of layers. Layers are added sequentially to construct the model. Architecture 1. The first LSTM layer with 100 neurons, LSTM100, expects an input shape of n steps, n features, and uses the ReLU activation function. The return sequences equals true parameter ensures that the output is a sequence, which is required when stacking LSTM layers. 2. The second LSTM layer has 50 neurons and does not return sequences. Return sequences equals false. This means that it will output a single vector as input to the next layer rather than a sequence. 3. A dense layer with 10 neurons is then added, which is a fully connected neural network layer. This is followed by another dense layer with a single neuron, which seems to be configured for a regression task given that the loss function used later is MSE, which stands for mean squared error. The model is then compiled using the Atom Optimizer, a variant of stochastic gradient descent, and is configured to use the mean squared error loss function, which is commonly used for regression tasks. The metrics parameter includes may or mean absolute error as a metric to monitor during training. In summary, the purpose of this code is to configure and compile a neural network model that can take a sequence of data with multiple features and predict a single continuous output value. It is suitable for regression problems involving time series or sequential data. The Python code snippet model.summary is typically associated with deep learning frameworks such as TensorFlow with keras or similar libraries where you define and work with models, especially neural networks. This method, when called on a model instance named model, provides a concise summary of the model's architecture. It outputs important details about the model's layers, including the name of each layer, its type, e.g. dense, conv2D for convolutional layers, LSTM for long short-term memory layers, etc., the output shape of each layer, and the number of parameters, weights, and biases that are part of each layer. The summary outlines both the trainable and non-trainable parameters, which helps in understanding the capacity and complexity of the model. Trainable parameters are those that the model updates during the training process, while non-trainable parameters are usually those that are kept static during training, such as parameters in layers that are frozen to prevent them from updating. The purpose of this code is to give the user a clear understanding of the model structure, which is particularly useful for debugging, optimizing, and validating the design of the neural network. By examining the summary, developers can ensure the model has been constructed as intended and make informed decisions about potential changes for performance improvements or computational efficiency. This Python code snippet is part of a larger code that involves training a machine learning model using a dataset. The focus of the provided code is on fitting the model to the training data and visually presenting the training process through a plot. The first line of the code is responsible for training a machine learning model. The model, which might be a neural network given the use of epochs often associated with neural networks, is trained on a set of input features X-train and corresponding target values Y-train. The training process iterates for a fixed number of rounds, referred to as epochs, in this case 100. During training, the model's performance is silently evaluated due to verbose equals 0 on both the training data and a separate validation dataset, which consists of X-test and Y-test. The use multiprocessing's true argument indicates that the training should be done using multiple CPU cores to speed up the process if possible. The purpose of this training step is to enable the model to learn the underlying patterns of the data so that it can make accurate predictions on unseen data in the future. Following the training, the code makes use of the matplotlib library to create a graphical representation of the training process. There is the creation of a new plot with specific dimensions set by fig size, and then two lines are plotted, one for the training loss and another for the validation val loss. These loss values are retrieved from the model's history, which keeps track of performance metrics over each epoch during training. Each line on the plot is labeled accordingly, using a legend, with the loss lines indicating how well the model is performing. Lower loss is generally better. Finally, a title is added to the plot, and it is displayed to the user with plt.show. Such a plot is commonly used to diagnose the learning process, particularly to check for overfitting or underfitting, and to determine if the model's learning is converging over time. This Python code snippet appears to be calling a function named evaluation from a module or package named functions. The evaluation function is used to evaluate a machine learning model by comparing its predictions ypred against the true values ytrue. It takes several arguments. X-test, the test set features that the model uses to make predictions. Y-test, the actual true labels or values that correspond to the test set features. Model, the trained machine learning model that will be evaluated. Random, a Boolean value indicating whether to randomly select a subset of the test set for evaluation. If set to false, this implies that the selection will be deterministic or in a particular order. Npreds, the number of predictions to evaluate. This could imply that only a subset of the test set will be used for this evaluation. Showgraph, a Boolean value indicating whether to display a graph of the evaluation results. When evaluation is executed, it returns three values which are subsequently stored in pred, ytrue, and ypred variables. Pred perhaps contains a structured output that may include various metrics or additional information about the evaluation process. Ytrue stores the ground truth values, the true labels or values for the test data provided by ytest, and ypred contains the predicted values generated by the model. The purpose of this code is to conduct an evaluation of a machine learning model's performance using specified test data and settings. An option to visualize the results with a graph is also provided, which can help in understanding the model's prediction accuracy and other evaluation metrics graphically. The provided Python code snippet is designed for creating a convolutional neural network CNN using Keras, a high-level neural networks API. The purpose of the code is to construct a machine learning model that can process sequential data for tasks like time series analysis, signal processing, or sequence prediction. At the beginning of the code, keras.backend.clear session is called to clear any existing models in memory. This is useful for starting afresh and avoiding potential conflicts with previously defined models. The next two lines extract the number of steps, time steps, and features variables at each time step from training data, assuming xtrain is a NumPy array or a similar data structure with at least two dimensions, one for the steps and one for the features. The model is initialized as a sequential model, which means that the layers are going to be added in sequence. First, a 1D convolutional layer is added using conv1d, which is designed to process one-dimensional sequence data. This layer will learn local patterns in the sequence. The filters and kernel size parameters determine the number of output filters and the size of the window to consider for each convolution operation, respectively, and ReLU is specified as the activation function to introduce nonlinearity. Following the convolutional layer, a max pooling layer with max pooling 1D reduces the dimensionality of the data by taking the maximum value over a window, helping to make the detection of features more robust. Data is then flattened using flatten to convert the multi-dimensional outputs from the previous layers to a single long feature vector, which is necessary before passing it to the fully connected layers. Two dense layers, dense, are specified next. The first dense layer has 5 neurons and uses ReLU activation, while the second has a single neuron output layer with no activation function. This is typical for a regression problem where the output is a single continuous value. Finally, the model is compiled with Atom as the optimizer and MSE mean squared error for both the loss function and the metric. This suggests that the model is being prepared for a regression task where the goal is to minimize the mean squared error between the model's predictions and the actual values. The Python code model.summary is typically used in the context of a neural network or machine learning library like TensorFlow or Keras. This method provides a concise description of the model that has been built, including the layers in the model, their types, the output shapes of each layer, and the number of parameters, weights, and biases in each layer and in total. When model.summary is called, it prints out a tabular representation of the layers, making it convenient to see the overall architecture at a glance. This is particularly useful for verifying the design of the model. ensuring that the dimensions align between layers, and for understanding the complexity of the model in terms of the number of trainable parameters. The method is often used after defining the model and before training it, as a sanity check to confirm that the model has been constructed as intended. The provided Python code appears to be using a machine learning framework, likely TensorFlow or Keras, to fit a model to some training data. The purpose of this code is to train a neural network or another kind of model on a given dataset and to visualize the training process. The model.fit function is training the model using xtrain and ytrain, which are the features and labels of the training data, respectively. The training process will run for 25 epochs, which means that the entire dataset will be passed through the neural network 25 times. The verbose equals 0 parameter indicates that no detailed logging output will be displayed during the training process quiet mode. Validation data is supplied in the form of x-test and y-test, which the model will use to evaluate its performance after each epoch. Setting use multiprocessing true enables the use of multiple cores for faster processing if possible. After the training is complete, the code plots the loss metric for the training set and the validation set. This is achieved by creating a figure with a specified size using plt.figure. The plot commands are then used to plot the loss values model history loss from the training and the validation loss values model history val loss. The term loss refers to the numerical value representing the error of the model, with lower loss indicating better performance. The val loss is the loss computed on the validation data, thus providing insight into how the model generalizes to unseen data. A legend is added with plt.legendLocals1 to distinguish between the two plotted lines, and plt.title gives the chart a title, conj training process. Finally, plt.show is called to display the resulting plot on the screen. This visual representation allows someone to quickly assess the training progress and detect issues like overfitting, where the validation loss starts to increase while the training loss continues to decrease. This Python code is calling a function named evaluation from a module named functions. The function is being provided with several inputs: x-test, y-test, model, and 3 named arguments: random equals false, npreds equals 50, and show graph equals true. The purpose of the code is to evaluate a given model's performance using a test dataset. The x-test parameter likely represents the features of the test dataset, while y-test corresponds to the true labels or target values. The model parameter probably holds a trained machine learning model that will be used for making predictions. The named arguments specify additional evaluation behavior. Random equal false might indicate that the predictions should not be randomly sampled but chosen in a specific manner. npreds equal 50 likely means that only 50 predictions will be evaluated. And show graph equals true implies that a graph, perhaps a performance graph, will be displayed as part of the evaluation. Upon execution, the evaluation function performs a series of actions to assess the model's prediction capabilities. It is expected to return 3 values that are being assigned to pred, ytrue, and ypred. These are likely the selected predictions made by the model pred, the true values for these predictions ytrue, and the model's predicted values ypred. These returned variables can then be used for further analysis to determine the quality of the model through metrics such as accuracy, precision, recall, etc. The presence of show graph equals true indicates that a visual representation of the model's performance will also be presented, which can be helpful for intuitive understanding of the results. The given Python code snippet is using the pandas library to concatenate a list or a sequence of data frame objects into a single data frame. The stocks variable presumably contains an iterable of data frame objects, each possibly representing stock information such as prices, volumes, or other financial data. The pd.concat function is a versatile tool in pandas used for combining data frames along a particular axis, by default axis equals 0, which represents rows. By setting ignore index equals true, the function is instructed to reset the index of the resulting data frame. This means that instead of preserving the original row labels from the source data frames, the new data frame will have a continuous integer index starting from 0. The purpose of this code is to amalgamate individual stock data frames into a comprehensive table, which subsequently facilitates the analysis or manipulation of the compiled data as a whole. This could be useful in scenarios where a user wants to perform operations on the combined dataset, such as sorting, filtering, or aggregating information across all the included stocks. The purpose of this Python code is to pre-process financial stock data for a machine learning task, typically to predict future stock returns. The code performs 2 main operations: scaling the data and preparing sequences for the purpose of training and testing a sequence prediction model, like LSTM, long short-term memory neural networks, used for time series data. Initially, the code uses a scaling function, most likely to normalize the features contained within the all stocks dataset. Normalization is applied within the range of 0 to 1. This is a common pre-processing step to ensure that all input features, e.g. stock prices, trading volumes, etc., contribute equally to the analysis, and it helps machine learning algorithms to converge faster. After scaling the data, the code prepares training and test sequences. It uses a custom function to perform this operation, which takes in the scaled stock data, target variable return, number of time steps, n steps that define the length of the input sequences, and a ratio to determine the train-test split. The n steps parameter most likely dictates how many time steps will be used to predict the subsequent return. The split parameter indicates that there is a need to split the data into training and testing datasets, and the ratio defines the proportion of the split, with 0.8 indicating that 80% of the data is used for training and the remaining 20% for testing. In summary, this code snippet normalizes stock data and then splits it into sequences necessary for time series prediction, preparing it for a machine learning model which would be used to forecast future stock returns based on historical data. The provided Python code is used to construct and compile a convolutional neural network CNN for a sequence processing task, such as time series prediction, using the Keras library. The purpose of the code is to define the architecture of the neural network, specify the optimization algorithm, and choose the loss function for training the model. Initially, the code clears any existing session in Keras, which can be a useful step to ensure that the model is started with a clean state. The dimensions of the input data are then determined by extracting the number of time steps, n steps, and the number of features, n features, from the training dataset, xtrain. These dimensions are necessary to configure the input layer of the network. The model is built sequentially, layer by layer. At the beginning, a conv1d layer is used with 500 filters and a kernel size of 10, which means it will process the input data by applying 500 different convolutional filters, each summarizing patterns over 10 consecutive time steps. The ReLU activation function is applied to introduce nonlinearity into the model. Following the convolutional layer, a max pooling 1D layer is added with a pool size of 10. It downsamples the input by taking the maximum value over each pool of 10 time steps, thus reducing the dimensionality and extracting the most prominent features from the convolved signals. The flatten layer then converts the pooled feature map into a one-dimensional array, making it possible to connect to a dense layer, which is a fully connected neural network layer. 3 dense layers follow, with the first 2 having 500 and 100 neurons respectively, both using the ReLU activation function. The final dense layer has a single neuron with a sigmoid activation function, which is often used for binary classification or regression tasks that output values between 0 and 1. Finally, the model is compiled with the ATOM optimizer and MSE mean squared error as the loss function. ATOM is a popular optimization algorithm that adapts learning rates for each parameter, and mean squared error is commonly used for regression problems. It measures the average of the squares of the errors, that is, the average squared difference between the estimated values and the actual value. To summarize, the code sets up a CNN for a regression or binary classification problem from sequence data, determines the architecture and layers of the model, and prepares it for training by compiling it with the appropriate optimizer and loss function. The Python code is related to training a machine learning model using a neural network or similar architecture supported by frameworks like TensorFlow or Keras. The first part of the code uses the .fit method to train the model on a set of training data. The xtrain and ytrain variables are the features and labels of the training data, respectively. The model is trained for 25 epochs, where an epoch is a full pass through the entire training dataset. The verbose equals 0 argument suppresses the output of training progress messages that are typically printed after each epoch. The validation data equal xtest, ytest means that the model's performance is also being evaluated on a separate test dataset after each epoch, and this is used to check that the model isn't overfitting to the training data. Use multiprocessing equals true implies that if possible, the training process will use multiple CPU cores to speed up the computations. The second part of the code involves plotting the training history to visually assess how the model's loss, a measure of how poorly the model performs, changes with each epoch. Loss values for the training data loss and the validation data val loss are extracted from the model's history object and plotted using matplotlib. A plot is created with a size of 16 by 4 inches. Two lines are plotted, one for the training loss and another for the validation loss. A legend indicating which line corresponds to which type of loss is displayed, and the entire plot is subsequently shown on the screen. The purpose of this code is to train a machine learning model and visualize its training progress to ensure that it learns effectively from the data without overfitting or underfitting. The plots are a common diagnostic tool to help developers understand how well the model is learning over time, and if necessary, adjust the training parameters. The provided Python code snippet appears to be invoking a function named evaluation from a module named functions to evaluate the performance of a machine learning model. The evaluation function seems to be called with several arguments, which include xtest, ytest, model, as well as a few keyword arguments, such as random true, npredx100, and showgraph true. The purpose of the code is likely to assess how well the model is performing by using test data, xtest for input features, and ytest for actual target labels. The model's predictions are compared against the true labels to determine its accuracy or another performance metric. The random true keyword argument suggests that the function might select a random subset of test data for evaluation, while npredx100 likely indicates that only 100 predictions will be evaluated. This subset could be representative in case the test dataset is too large to process entirely, or if the evaluation is computationally expensive. By setting showgraph equals true, the code hints at a visual component where the function will generate and display a graph representing the results of the evaluation. This could be a confusion matrix, ROC curve, precision recall curve, or any other visualization that helps interpret the model's performance. The function then returns three values, pred, ytrue, and ypred, which probably represent a selected subset of model predictions, the corresponding true values from the dataset, and the complete set of predictions made by the model, respectively. These returned values could be used for further analysis or reporting on the model's evaluation. The Python code provided defines a function called createModel that builds, compiles, and trains a convolutional neural network CNN using Keras, a high-level neural networks API. The purpose of this function is to create a CNN model for time series or sequence data prediction. The function starts by clearing any existing TensorFlow backend session to make sure the model starts with fresh parameters. It then converts the provided parameters, which are expected to include dimensions for dense layers, the number of filters, pooling size, and kernel size, into integer values. The model is sequential, meaning that layers are added in a linear stack. It includes a 1D convolutional layer with a specified number of filters and kernel size, designed for sequence input. This is followed by a max pooling layer to reduce dimensionality and help the model to focus on the most salient features. The data is then flattened to transform the 2D feature maps into a 1D vector suitable for input into the dense layers. Two dense fully connected layers follow with specified dimensions and ReLU activation functions for nonlinearity. The model's output layer consists of a single neuron, since this seems to be a regression problem indicated by the MSE loss function, which stands for mean squared error. The model is compiled with the Atom optimizer and is trained on provided training data, xtrain and ytrain, for 4 epochs, with validation on test data, xtest and ytest. Multiprocessing is enabled during training for potential performance improvements. Finally, the model is evaluated on the test data, returning the test mean squared error score, which quantifies how well the model predicts the target variable. The primary purpose of this code is to facilitate the quick creation and evaluation of a 1D CNN model for regression tasks given input and target data. The return value can be used to assess the prediction accuracy of the model on unseen data. The given Python code defines a function Bayesian optimization that applies Bayesian optimization to the problem of finding the optimal parameters for a certain model, presumably a neural network or a machine learning model. Bayesian optimization is a strategy for finding the maximum or minimum of an objective function that is expensive to evaluate. In the function body, the first step is to define the parameter bounds p-bounds. This is a dictionary that maps each parameter to a tuple, representing the lower and upper bounds within which the Bayesian optimization should search. The parameters are filters, D1, D2, kernel, and pool, each having their respective numeric range defined. An optimizer object is then created from the Bayesian optimization class. This object takes as input a function createModel, which it will optimize, the parameter bounds p-bounds, a random state, for reproducibility of results, and a verbose level, which determines how much information is printed during optimization. The optimizer then runs by calling its maximize method, which takes two arguments, init points and niter. Init points denotes the number of randomly chosen points to evaluate before applying the Bayesian optimization process, while niter is the number of iterations for the optimization process after the initial random points. Thus, the optimizer will perform a total of 10 evaluations of the create model function, 5 initial random ones, and 5 guided by the Bayesian optimization algorithm's results. Finally, after the optimization is complete, the code prints the best set of parameters found by the optimizer by accessing its max attribute, which holds details of the optimal parameters and the corresponding value of the objective function. The purpose of this code is to automate the process of hyperparameter tuning for a machine learning or neural network model, which can often be a very time-consuming and trial-and-error-driven process. Bayesian optimization helps in selecting the best hyperparameters more efficiently by using a probabilistic model to predict the performance of the model with different hyperparameters and intelligently exploring the search space. This Python code snippet is designed to pre-process financial time series data, specifically for stock price prediction of Tesla TSLA. The purpose of the code is to normalize the stock prices, create sequences to be used for training a machine learning model, and then split this data into training and testing sets. Firstly, the series of TSLA stock prices is scaled between values 0 and 1. Normalizing the data is crucial in many data-driven applications, especially in machine learning, as it can lead to faster convergence during training and improved model performance. Following the scaling, sequences are generated using a specified number of time steps, n steps. These sequences are used as input features to predict future stock returns. The way these sequences are generated can be important for capturing temporal dependencies in the data, which is key for accurate predictions in time series analysis. Finally, the generated sequences are split into two sets, a training set and a testing set. A common split ratio like 80-20% in this case is used to ensure that there is enough data to train the model while also retaining a separate portion of data to evaluate the model's performance. The training set is used to fit the model, and the testing set is used to assess how well the model generalizes to unseen data. The Python function Bayesian optimization likely refers to a procedure for optimizing a black box function using Bayesian optimization techniques. Bayesian optimization is a strategy for finding the minimum or maximum of a function that is expensive to evaluate. It is especially useful when the function does not have an analytical form or its derivatives are not known. The core idea behind Bayesian optimization is to use a probabilistic model, such as a Gaussian process, to represent the unknown function based on observed data points. The algorithm iteratively selects the next point to evaluate by balancing exploration sampling, where the model is uncertain, and exploitation sampling, where the model predicts high performance. The function Bayesian optimization would take some parameters as arguments, which could include the following. 1. The black box function to be optimized. 2. The bounds for the input parameters domain of optimization. 3. A budget that limits the number of function evaluations. 4. Possibly some initial points to start the optimization. 5. The acquisition function that guides where to sample next based on the probabilistic model. The purpose of this code is to provide an efficient way to optimize a target function that is costly to evaluate. By utilizing Bayesian optimization, the function is able to suggest the most informative points to evaluate, potentially reducing the number of iterations needed to find an optimum and saving resources when compared to brute force methods such as grid search or random search. As the name implies, this code is based on Bayes' theorem, which updates the probability for a hypothesis as more evidence or information becomes available. The optimization procedure is used in various fields, from machine learning hyperparameter tuning to engineering design problems. The Python code in question is used to define and compile a convolutional neural network CNN model using the Keras library, which is a high-level neural networks API, capable of running on top of TensorFlow, CNTK, or Theano. The purpose of this code is to prepare a model for a machine learning task, likely to predict or classify data based on historical examples training data. Initially, the code defines the number of steps and features which are derived from the training dataset, referred to as X-train. These may correspond to the sequence length and the number of distinct features in a time series or sequence dataset, respectively. The code then proceeds to reset the state of the neural network by clearing the session. This is necessary to ensure that the model is trained from scratch without any leftover data from previous models that may have been created in the same session. A sequential model is instantiated, which implies that the neural network layers are stacked linearly. The first layer is a one-dimensional convolutional layer, conv1D, which is commonly used to extract features from sequence data like time series, audio, etc. It specifies the number of filters and kernel size for the convolution operation and uses the ReLU activation function. Next, the model applies max pooling 1D to reduce the dimensionality of the output from the convolutional layer, which helps in reducing the computation as well as potentially avoiding overfitting. The output is then flattened into a one-dimensional array to transition from the convolutional layers to fully connected layers. A dense layer with 250 nodes is added, again using the ReLU activation function for high-level feature learning. It is followed by another dense layer with 10 nodes, and finally, a single-node output layer for regression output, since no activation function is specified and the loss function is mean-squared error. The model is compiled with the atom optimizer and mean-squared error, MSE, as the loss function, which suggests that the model is being designed for a regression task where it will predict continuous values. The mean-squared error is also used as a metric for training, which will be useful to track how well the model is predicting during the training process. The code in question performs the training and evaluation of a machine learning model using Python, likely with the help of a deep learning library such as TensorFlow or Keras. Initially, the code trains the model by calling the .fit method on it. It passes in a set of training data, xtrain, and corresponding labels or target values, ytrain. The model is set to train for 100 epochs, meaning it will work through the entire dataset 100 times to optimize its parameters. Verbose output has been disabled, verbose equals 0, which means the method won't output logs about the training progress. Validation data, xtest, ytest, is also provided, which the model will use to gauge its performance on data it hasn't seen during training. By setting use multiprocessing equal true, the code indicates that it wants to use multiple CPU cores to parallelize data processing if possible, potentially speeding up the training process. After training, the code generates a plot to visualize the training and validation loss over each epoch. This visual representation helps to monitor how well the model is learning and whether it is overfitting or underfitting to the training data. Loss is a measure of how far off the model's predictions are from the actual values. A separate figure with a specified size is created to plot the training loss and the validation loss val loss. A legend is included for clarity, and the plot is shown on the screen. Finally, the model is evaluated by comparing its predictions against the actual test data. This is carried out by a custom evaluation function, which seems to be imported from a functions module. The evaluation function is perhaps calculating performance metrics or creating further visualizations. It returns three objects, pred, ytrue, and ypred, which represent the model's raw predictions, the true labels, and the predicted labels, respectively. The function is called with a subset of 100 randomly chosen test samples, random equals true, npreds equals 100, and is configured to also display a graph, show graph equals true. The specifics of the evaluation method are not described, but it appears to be a part of the assessment of the model's predictive ability. The given Python code is used to visualize and compare patterns in stock return values using the matplotlib plotting library. The script is tailored to create a line chart displaying fluctuations in return values of a specific stock, presumably Tesla TSLA, over a range of days. The script starts by setting up the figure size to ensure the plot is sufficiently large for viewing, 16 inches wide by 5 inches tall. It then adjusts the visual style of the plot to Seaborn White Grid, which is a theme that provides a white grid background with Seaborn styling enhancements for better aesthetics. Two sets of data are then plotted on the graph. The first line represents the stock's returns over a range of 100 days, from the 2000th to the 2100th entry in the stock's dataset. The second, highlighted line, represents a shorter range of 9 days, from the 2001st to the 2010th entry. This second line is probably used to highlight a specific pattern over those 9 days, and is made to stand out by having a larger line width and a different color than the first line. The plot is made more informative and easier to understand by including a legend that describes both lines, and by using descriptive labeling and titles. The legend is enhanced with visual properties such as a frame, fancy box, and transparency settings. The title patterns in testing set and the y-axis label return clearly indicate that the chart is analyzing patterns in stock returns within a testing dataset. Finally, the plot is displayed to the user using plt.show. The overall purpose of this code is to provide a clear, visual representation of stock return patterns over selected time intervals, which can be very useful for financial analysis or presenting insights in a visually accessible format. This Python code snippet is designed to test the predictive capability of historical binary patterns in stock return data for Tesla TSLA. Firstly, it converts the stock return values to a binary format using a function. It then divides the binary return array into two parts, a training set and a test set, using the first 2,000 entries for training and the rest for testing. The code looks for patterns of length 9 as defined by the step variable within the binary test data. For each pattern found in the test data, it compares this pattern against all possible patterns of the same length in the training data. When a matching pattern is found in the training data, the index of that pattern is stored. Next, the code searches for the value that immediately follows each matching pattern in the training dataset. This is the check step, which is equivalent to the pattern length plus 1. It does this with the aim of predicting whether this subsequent value will be a 0 or 1. The code aggregates these subsequent values for all matching patterns and uses the average to make a prediction. For each test pattern, the code compares the actual subsequent value to the predicted value. If they match, it adds a 1 to the total predictions list, signaling a correct prediction. Otherwise, it adds a 0, indicating an incorrect prediction. After iterating through the test data, the code calculates the accuracy of the predictions as the ratio of correct predictions to the total number of predictions made. Finally, it prints the accuracy to provide insight into how well the pattern matching strategy worked. It's important to note that the accuracy calculation only covers 10 instances due to the range limitation in the iteration. This is a very small sample size, and the actual predictive power may not be statistically significant. In a full-fledged application, you would want to test the approach on a much larger dataset to gain insights into its real-world effectiveness. This Python code snippet seems to be designed for pattern matching within a financial dataset, specifically for finding occurrences within stock return data where the pattern matches a given sample. Initially, variables are set up, a starting index start, a window size window, and an empty list A. A sample pattern from binary test is taken based on the starting point and window size. The code then enters a loop to scan a larger dataset binary train, checking each slice of the data against the sample. It uses accuracy score to perform this comparison, likely to mean that it checks if the selected window in binary train is identical to the sample. When a match is identified where the accuracy score returns a value of 1.0, the index of where this match occurs is appended to list A. After the loop, the code proceeds to visualize the findings. It uses matplotlib as implied by the Pelty object to plot a figure. This graph will show the original sample pattern from binary test plotted against the stock return values of Tesla indicated by TSLA. The true pattern is plotted with a specific line style, line width, and color. For each matching pattern identified earlier, the code then plots these onto the same figure, overlaying them on top of the true pattern for visual comparison. Finally, the graph includes a horizontal line at y equals 0, a title, labels for the x and y axes, a legend, and uses plt.show to display the graph on the screen. The purpose of this code is to help visualize where certain patterns of stock returns for Tesla match a specified sample pattern within a larger dataset. This can be useful for financial analysis, pattern recognition, and predictive modeling. Note, since the code provided has some context-based assumptions, and it seems to use variables and functions not defined within the snippet, the exact functionality might slightly differ based on the full context and environment in which this code is run. This Python code is intended to visualize and compare stock return patterns using the matplotlib library, which is commonly used for creating 2D graphs and plots in Python. The script appears to plot time series data related to the stock returns of Tesla TSLA over a specific period. It creates a line plot showing Tesla's stock returns from the year 2000 to 2020 and highlights a particular pattern in the returns from 2001 to 2011. In this plot, the stock return data for different periods is styled differently to distinguish amongst them. A 9-day return pattern is highlighted with a thicker line and a distinct color to make it stand out. In addition to this pattern, individual data points representing the stock return on the last day of this 9-day window are marked with a specific symbol and color. The script then iterates through a list of starting indices A, extracts a 10-day return pattern starting at each index, overlays it on the plot, and marks the return on the 10th day in each of these patterns with a symbol to compare these to the highlighted pattern. A horizontal line at 0 on the y-axis is drawn to provide a reference point, distinguishing between positive and negative returns. The legend is customized and placed on the plot to help identify the different elements shown. A title and a label for the y-axis are set to show what is being depicted, namely the stock returns of Tesla and the attempts to match a particular pattern previously identified in the training set of data. Finally, the plot is displayed to the user using the show function, allowing for visual analysis and comparison of the stock return patterns. This line of Python code appears to be calling a function related to algorithmic trading using the moving average convergence divergence MACD indicator, a popular tool in technical analysis for identifying potential buy or sell signals based on the momentum of security prices. The function named MACD trading is being called with a subset of data from a data frame stocks that is presumably indexed by ticker symbols, in this case TSLA for Tesla. The .loc 2018-18 part suggests that the function is being given stock data limited to the year 2018. The MACD trading function is part of a module named functions, indicating that the code for this function is organized within a separate file or library, which includes various functions, and it has been imported before this line is executed. This function is expected to return two items, likely a tuple, which is getting unpacked into the variable's profit and trades. The variable profit would typically represent the financial gain or loss resulting from the trades executed following the MACD strategy within the specified time frame. The variable trades most likely contains information about the individual trades that were executed, such as the dates, quantities, and prices of the stocks traded. In summary, the primary purpose of this code is to apply a MACD-based trading strategy to a specific set of Tesla stock data from the year 2018 and unpack the resulting performance metrics and trade details into the variables profit and trades. The provided Python code indicates that it is calling a function or method makeD from a plotting module or library and passing in a subset of data from a variable named stocks. The data being passed is filtered to include only the entries related to the stock symbol, TSLA, presumably Tesla, and is further limited to data from the year 2018 by using the .loc 2018 indexer. The purpose of the MACD function is not fully described by the code snippet itself, but its name suggests that it may be used to compute and plot the moving average convergence divergence MACD, which is a trend-following momentum indicator that shows the relationship between two moving averages of a security's price. The MACD is typically calculated by subtracting the 26-period exponential moving average EMA from the 12-period EMA. In summary, the code is intended to perform analysis on Tesla's stock for the year 2018 by calculating the MACD indicator and possibly plotting it on a graph. This analysis is commonly used in technical analysis by traders who want to identify potential buy or sell signals based on the momentum and the relationship between different moving averages. The Python code snippet processes financial data related to stocks by applying a trading strategy named MACD, moving average convergence divergence, and evaluates the performance of this strategy. First, the code creates a list called companies that is a copy of some other list named stocks. Then, an empty list called returns is initialized to store the performance metrics of the trading strategy for each stock. Next, a for loop iterates over the stocks list. Inside the loop, it calls a function MACD trading from a module named functions. This function presumably implements the MACD trading strategy. It takes a slice of each stock's data for the year 2018, a budget of 5,000 units, and two flags for controlling the display of graphs and returns, show graph and show return. Both are set to false, meaning no graphical output or display of returns is generated. For each stock, the MACD trading function returns two values: profit, which indicates the monetary profit obtained by applying the buff strategy with the specified budget, and trades, which could represent the number of trades made or the actual trades performed, though the trades variable is not used further in the provided code snippet. After calculating the profit, the code appends the percentage profit as a percentage of the initial budget to the returns list. This is done by dividing the profit by the initial budget, 5,000, multiplying by 100 to get the percentage, and rounding it to 2 decimal places. In summary, the code's purpose is to simulate the MACD trading strategy on a set of stock data for the year 2018, evaluate the profits in terms of percentage gain on the initial budget for each stock, and store these performance metrics in a list. The result is a list of performance measures that could be used to compare how well the strategy performed across different stocks. The Python code snippet is using the pandas library to create and manipulate a data frame, which is a two-dimensional labeled data structure with columns of potentially different types. The purpose of this code is to organize and sort financial return data for a list of companies. The code first constructs a data frame with two columns, company and return percent. The company column is filled with data from the company's variable, and the return percent column is filled with data from the returns variable. These two variables are expected to be lists or arrays of equal length, where each company name is associated with its corresponding financial return percentage. After creating the data frame, the code sorts it by the return percent column. The sort values function is used for this purpose, with the by parameter specifying the column to sort by. The ascending equals false argument indicates that the sorting should be done in descending order, meaning the company with the highest return percentage will be at the top of the data frame. The end result of this code is a neatly organized data frame displaying companies and their associated returns, sorted from the highest return to the lowest. This can be useful for financial analysis, allowing users to quickly identify top-performing companies in terms of return percentage. The line of Python code you've presented seems to be part of a larger code related to stock trading, specifically regarding Tesla TSLA stock. The code calls a function BB trading from an imported module named functions. This function appears to be designed to implement a trading strategy based on Bollinger Bands, which is a common technical analysis tool used to determine overbought or oversold conditions in a stock market. The stocks is a data structure, most likely a pandas data frame, that contains stock market data. The code stocks TSLA, 2018, is accessing the data for Tesla TSLA stock specifically for the year 2018. This function BB trading takes three arguments. The first argument is the data for TSLA stock in 2018, and the other two arguments U equals 0.03, L.03, likely represent the upper and lower threshold parameters for the Bollinger Bands. An upper threshold of 0.03 and a lower threshold of 0.03 suggest that the function should signal trades when the stock price is 3% above the upper band or 3% below the lower band. The function returns two objects, profit and trades. These likely represent the total profit or loss generated from the strategy during the specified period and the details of each trade executed by the strategy, respectively. Profit could be a number indicating the financial outcome, while trades might be a list or data frame containing records of each trade buy-sell made by the algorithm. The code snippet provided is a simplified Python script that appears to be part of a larger stock trading analysis code. The purpose of this code is to calculate and collect the percentage returns of a trading strategy applied to a set of companies over the year 2018. The first line creates a list of company identifiers or potentially stock symbols from an existing collection called stocks. It essentially copies the stocks collection into a new list called companies. Subsequently, it initializes an empty list named returns, where it will store the calculated percentage returns for each company. In the following lines, the code iterates over each company present in the stocks collection, which likely contains historical stock data. For each company, it applies a trading strategy encapsulated by the functions.bb trading function. This function takes a slice of the company's historical data from the year 2018 and some additional parameters, including a budget constraint, budget equal 5,000, upper and lower thresholds for trading U equal 0.03 and L equals 0.03, and flags to determine whether to display graphs or return values, show graph equals false, show return equals false. The function's BB trading function appears to simulate the trading strategy and returns two values, the profit from the trades made and the number of trades executed, although the latter is not used in further calculations. For each company, the code computes the percentage profit compared to the initial budget of 5,000 by dividing the profit by the initial budget of 5,000 and then multiplying by 100 to convert to a percentage. This result is rounded to 2 decimal places and added to the returns list. At the end of this script, the returns list contains the performance metrics, percentage profits for the trading strategy applied to each company's stock data over the given period. This might be used to evaluate how well the trading strategy performed across different stocks, or to compare the efficiency of various strategies. This Python code snippet is designed to create and manipulate a pandas data frame for the purpose of organizing and presenting data related to companies and their respective returns, expressed in percentage. Firstly, it creates a pandas data frame which is a two-dimensional, size-mutable, and potentially heterogeneous tabular data structure that allows for data manipulation and analysis. The data frame is created with the help of a dictionary where the keys are the column labels here, company, and return percent, and the values are the lists containing the data here, companies and returns, which are variables assumed to contain lists of companies' names and their returns in percentages respectively. After the data frame is constructed, the sort values method is called on the data frame to sort the data. The sorting is based on the values in the return percent column as specified by the by parameter. The ascending equals to false argument indicates that the sorting is to be done in descending order, meaning that the company with the highest return will be placed at the top of the data frame. The purpose of this code is to provide a sorted view of companies and their financial returns, allowing for a quick and easy way to see which companies have the highest returns. This can be particularly useful for financial analysis, investment decision-making, or for any scenario where one needs to rank companies based on their performance as indicated by their returns.